All right, there are really four basic equations that sum up all of classical electricity and magnetism. You've already learned a couple of these. You learned about Gauss's law of electricity, which you know is the closed integral E dot dA, that is flux, is equal to Q enclosed divided by epsilon naught. All right, we knew that as Gauss's law. And there is also, though, Gauss's law of magnetism. Gauss's law of magnetism we talked about briefly, and that one is B dot dA is equal to 0. There is a third law that we're going to talk about, but technically speaking, this law is not Maxwell's equations. Maxwell took this law we're about to talk about and modified it some, and then it became one of Maxwell's equations. So now we want to turn our attention to Ampere's law. Now we're going to use analogies here a lot to talk about Ampere's law and to introduce it. For example, when we talked about electric field, we came up with an equation that looks something like this. So this is a vector equation, and you know, this is stuff that you should be familiar with at this point, but we used this to derive equations for complicated charge distributions, to derive equation for the electric field. But we also expressed electric field, or derived electric field, generally from Gauss's law. Okay, so it can be said that Gauss's law is a more generalized expression of this equation here. Now, if we take that idea and we apply it to the world of magnetism now, you've been introduced to the BS law. And it's of this form. So the magnetic field can be found for some type of current distribution by using this right here. But to express it more generally, we'll write it this way. Okay, this is Ampere's law right here. So this was Gauss's law, the more general expression. This is Ampere's law, the more general expression of the BS law. There are two other Maxwell's equations. I shouldn't say two. There's one other Maxwell's equation that will come along. Remember, Ampere's law is really an unmodified Maxwell equation. Maxwell took this and added another term out here, and then that became Maxwell's equations. One of the third of the four Maxwell's equations. But later on, we will introduce the fourth of Maxwell's equations, which is Faraday's law of induction. And we'll get there eventually. All right, but we're going to use analogies then between Gauss's law and Ampere's law to fully disclose exactly the way Ampere's law works here. For example, in Gauss's law, we had the concept of a Gaussian surface. And we said, here's this imaginary Gaussian surface. It has to have a charge enclosed in order for it to be useful to us. But this was a three-dimensional closed surface, and it was enclosing the charge. Okay. For Ampere's law, we're not going to have a closed surface. Instead, we have something called an Amperian loop. Now, let's think about why is that a surface and this a loop. Well, look back here at the equations. When we dealt with Gauss's law, we were dealing with a closed integral over an area. So this was a closed surface integral. So our Gaussian surface was a three-dimensional surface. Here, the ds stands for a line. So this is going to be a line integral, but it is a closed line integral. Well, what is a closed line then? Well, a closed line is a loop. So even though it may look the same as a Gaussian surface, we drew our Gaussian surfaces like this. We may draw our Amperian loops like that. This one is three-dimensional. This one is going to be two-dimensional. Now, just like up here, the Gaussian surface did not have to be a nice smooth circle. It could be literally any shape whatsoever as long as it's three-dimensional. The same down here. The loop in general can be any shape whatsoever, but it's really only going to be useful to us if we can figure out what its circumference is. Up here, we needed to have a nice general surface so that we could figure out easily, to get a direct solution for Gauss's law, we needed to easily be able to compute the surface area. Well, down here, because we're talking about a line integral and a closed loop, we need to be able to determine the circumference of that loop, or the length of that material around the 2D surface here. Okay, so what does that mean? That means circles, rectangles, perhaps triangles or squares. Those sorts of things are going to be the best for a 2D loop, while up here, for our 3D surfaces, we had spheres, we had cubes, we had cylinders, those sorts of things. You get the analogy here that we had surfaces that were 3D, and now down here we're going to have loops that are 2D. Okay? Be careful when you look at these on a piece of paper, they look the same, but they're not the same. All right, also from Gauss's law, the right-hand portion of that equation, this right here, was the net enclosed charge. Over here on the right-hand side, we don't have a charge, we have a current. And that current is going to be the net enclosed current. Okay, up here, it was the net enclosed charge inside our Gaussian surface. Down here, it's going to be the net enclosed current inside our Amperian loop. So there's another analogy that goes along with Gauss's law and Ampere's law. But what that means is that we have to figure out a way to determine whether a current is positive or negative inside of our loop. So here's the way we're going to do it. For charges, by the way, it was real easy. You either had a positive charge or a negative charge, and you just summed them all up. Well, down here, you can have positive currents and negative currents, but how do you determine what's positive and negative inside of a loop like this? Well, let me explain. Let's say that we have an Amperian loop here, and we have a current that's going in at this point right here. So there's the X that indicates we have a current going in. Let's call that I1. Over here, we have another current that's coming out of the page, and we'll call that I2. All right. Which one of those is the positive current and which one is the negative current? To be honest, it can be either one, but whether or not you call something positive or negative doesn't depend upon you just choosing it. It depends upon the direction in which you traverse this loop here. So let's say, for example, that you're traversing the loop in this direction, like that. The loop can be any shape, remember, and you can traverse it in any direction. But once you decide on your direction, then you're going to use the right-hand rule to determine which of these is positive and which of these is negative. What do I mean by right-hand rule? Well, you remember, grab the wire. Well, put your fingers in the direction of that loop, the direction you're going to traverse the loop. Your thumb then points in the direction of the positive current. So this one would be positive and this one would be negative if we're traversing the loop in that direction. Conversely, if we traverse the loop in this direction, then in is going to be positive and out is going to be negative. Now it's important that you keep that sign convention because the direction in which you traverse the loop then determines whether your currents are going to be positive or negative. All right? Okay, one other thing regarding an analogy between Gauss's law and Ampere's law is this. A lot of times when you worked problems and you found, maybe you had spherical symmetry, it turned out that you ended up with a lot of 1 over 4 pi epsilon naught kinds of things in it. Or maybe you had a 1 over 4 pi r. 1 over 4 pi r squared. Where did that come from? Well, that came from the spherical symmetry here. And oftentimes that would show up. That 4 pi then you often moved over and it became part of this this constant that we called k here. Well, when we get to Ampere's law, you're going to discover that 1 over 2 pi r shows up, all right, for circular symmetry. Well, what does that mean? Where does that come from? That's the circumference of a circle. That's all that is. So this is going to show up a lot in our Amperian loops when we use Ampere's law, the same way that 1 over 4 pi r squared showed up a lot when we use Gauss's law. So the 4 pi came about because of the symmetry of the situation. Well, the 2 pi is going to come about because of the symmetry of the situation as well. All right? All right, so let's now use Ampere's law to solve a problem. Just like Gauss's law, when we used Gauss's law, we derived equations for electric fields. We're going to use Ampere's law to derive equations for magnetic fields. And we already have derived, using the BS law, the magnetic field for a long straight wire. It's mu naught I over 2 pi r. The idea, the idea was that here's this long straight wire, it's carrying a current I in that direction, and out here some distance r away at a point P, the strength of the magnetic field is given by this equation. We derived that in a previous video using the BS law. Well, now we're going to do the same thing and derive that expression, but we're going to use Ampere's law. And here's the way we have to do this. Let's say that here is our current carrying wire, and we're looking at the current coming out of the page here. So this is the wire right here, the current's coming out of the page. And let's call that current I naught. Then what we want to do is we want to go out here some distance away from the center of the wire, some distance r, to some point P, and we want to know what is the magnitude of the magnetic field at that point right there. And not just the magnitude, but also the direction. We can figure that out as well. What's the direction? Well, here's the way that we'll figure this out. First thing is we need to draw our Amperian loop. We remember when we worked Gauss's law problems, one of the first things we had to learn to do was to draw the Gaussian surface and to choose the correct geometry. Well, now we need to choose the correct geometry for our Amperian loop in this case. And in this case, it's going to be a circle with the wire at the center, and it has a radius of r. So if I could have drawn a perfect circle, the wire would be in the center of the circle and the radius would be r. Now, which direction do you want to traverse the loop? I'll give you a hint. You want to traverse your loop in such a direction so that that current right there is considered positive, and that way you don't have to worry about the sign. So we're going to traverse our loop in the counterclockwise direction that you see here. So that means that when we go around this loop, our ds vectors are going to point like that. And over here, our ds vectors would point like this. Down here, ds vectors would point like that. So we're going to go all the way around the loop, traverse the loop, and divide it up into little sections, and those are going to be our ds vectors. So we've decided upon the direction of our traverse at this point. All right? Then, let's use our right-hand rule to figure out that I is positive coming out. All right, great. And now we need to decide how many currents are coming out. Well, there's only one here. It's really obvious. There's only one, and it's I naught. All right, so now that we've decided all that, let's write down Ampere's law. Here it is. Closed integral b dot ds is equal to mu naught times I enclosed. All right, well, what's the I enclosed? The I enclosed is just our I naught. At that point, we're finished with the right-hand side. So we're working the sides of the equation now the same way we did for Gauss's law. The right-hand side is done, and it's just going to be mu naught I naught. All right, now we're ready to do the left-hand side. And the left-hand side is a dot product, so let's go ahead and break up the dot product. It's still a closed loop, b cosine theta times ds. Okay, now I can get rid of those vector signs. I've made the dot product, so those should be gone. Ignore those blobs above the b and the s there. All right, the cosine term is the angle between b and ds. We know the direction of ds here. What about the direction of b? Well, you find the direction of b the same way. You grab the wire, you put your thumb in the direction of the current, and then the magnetic field lines are going to be in that direction, around like that. So what does that mean? That means out here at this Amperian loop, the b vectors are going to be in the same direction as the ds vectors. Regardless of where you're at, on any side, the b vectors and the ds vectors are pointing in the same direction. Okay, so what does that mean? The angle between the b and the ds is going to be 0. And is it that way everywhere on the loop? Yes, it is. If that is the case, then this cosine term is a constant, and we can factor it out of the integral. And it's going to be 1. Okay? Now, ask yourself the next question. Is b constant everywhere on my Amperian loop? If the answer is yes, then b is also a constant, and you can factor out b. And of course, in this case it is, because we're the same distance away from the center, the same distance r, everywhere on the Amperian loop, so b is a constant. So this leaves b, closed integral ds, is equal to mu naught I naught. All right, now this closed integral ds, what is that? Well, that is the length of the line that makes up our loop. And in this case, since we've chosen a circle as our Amperian loop, this is just the circumference of our circle. So this is going to be b times 2 pi r is equal to mu naught I naught. Okay, we've worked the left side of the equation now. Now all that's left to do is to solve. And when we solve that, we're going to solve for b. B is equal to mu naught I naught over 2 pi r, which is what we expected it to be. So let's celebrate. Ta-da. All right, that one was easy. We knew what we were going after. but I showed you how to use Ampere's law to figure it out. And that was outside of the wire. What about if we go inside of the wire? Okay, let's do that. Let's figure out the magnetic field inside of the wire. So once again, we've got a long straight wire. Once again, this, now we've zoomed in, this is the wire, and the current is coming out. So this is the actual radius of the physical wire itself. And the entire current coming out is I naught. All right, well, we want to figure out what the magnetic field is inside of the wire. So anywhere between a radius of 0 to big R is the region that we're interested in. So let's pick an Amperian loop that is inside the wire, and it has a radius, some arbitrary radius, R, that is between 0 and big R. That places it inside the wire. Okay, now the question becomes, if we write down Ampere's law, B dot ds is equal to mu naught times I enclosed, the question becomes, when we work this, what is I? What is the I enclosed? We know the entire current going through that wire and coming out of the page is I naught, but what is the current that's enclosed inside my Amperian loop? Obviously, that's not the whole thing. Well, here we rely upon something that we already have a definition of, and that is current density, J. Current density is the current per area. So the current per area. Now, J in this case is going to be the total current, I naught, divided by this total area, which is just going to be pi big R squared. That's what J is. If I naught is known and big R is known, that's the radius of the wire, then this quantity could be computed. But since J is a current density, it's like, it's a density, so it's going to be a constant for the amount of current that, let's call I sub A, the current that's inside my Amperian loop, divided by the cross-sectional area of my Amperian loop, which is just going to be pi little r squared. So this I sub A, that's the amount of current that's enclosed inside my Amperian loop. That's what this variable is. That's what we want. So we can take this relationship here, and we can solve for I sub A. And when we do that, let's see, I'm going to get pi little r squared I naught over pi big R squared. The pi's will cancel, and I sub A, which is I enclosed, is going to be R over big R quantity squared times I naught. So that's the amount of current that's enclosed inside our Amperian loop. So let's take our equation now, bring it down here, closed integral. Let's go ahead and separate the dot product. B cosine theta ds is equal to mu naught times I enclosed, which is R over big R squared times I naught. Okay, we're finished with the right-hand side at this point. Let's work on the left-hand side. All right, when we get to the left-hand side, we have to do the same sort of thing that we did previously. It is only the current that is enclosed that matters, not the current that is outside of our Amperian loop that matters. We have the current coming out of the page, so let's pick the direction in which we traverse this loop as being in that direction and that direction. So the ds vectors point along that path there, and the b vectors also are going to point along that path. So what's the angle between the b and the ds? It's 0. Now, you got to convince yourself, is it that way everywhere along this path? And the answer is yes. So that means the cosine term is going to be 1. It is constant everywhere along the loop. You can factor it out. Same for b. b is also going to be constant along the loop. Why? Because the loop is chosen in such a way that it is centered in the wire. So b is constant. We'll factor it out. Closed integral ds is equal to this stuff on the right here. All right, what is closed integral ds? That's the circumference of our loop. So that's just 2 pi r is equal to mu naught r over big R squared times I naught. All right, the next step is solve for b. b equals mu naught I naught times r over 2 pi big R squared. There. All right, this isn't exactly the same thing as this. This was inside the wire. This is, I'm sorry, I did that backwards. This is outside the wire. This is inside the wire. So big R here is a constant. It's little r that's the variable. And you can see this is a straight linear relationship. Everything here inside that loop there is a constant for our problem. So little r is the only variable, and it ranges between 0 and big R. Whereas over here, little r is the variable. Everything else besides little r is a constant for our problem. So this is a 1 over r relationship, and this is a linear r relationship. So if you were asked then to graph the magnetic field for all radii between 0 to infinity, and this right here represents the edge of the wire, big R, then on the inside of the wire, it's a linear relationship. It's directly proportional to R, so it's going to be a straight line that goes up like that until you get here to big R. And then after that, the relationship becomes a 1 over R relationship. So that falls off and looks like this and reaches 0 in the limit. So this one is a 1 over R relationship. This one is just an R relationship. Okay? That would be a good exercise for you to know how to do, is how to determine the magnetic field inside and outside of a long current carrying wire and be able to graph it something like this. You could determine what that value is on the vertical axis right there by setting these two things equal to each other. You know that they have to be equal to each other in order for that to happen. So that turns out that at that point right there, it's mu naught I naught over 2 pi big R. So that's right at the edge where little r equals big R. Okay. That's about all I want to talk about regarding Ampere's law. Let's now take that information and let's talk about solenoids. A solenoid is just a coiled up loop of wire that carries a current. You can think of it as a slinky. It's a slinky carrying a current like that. It's usually very tightly bound. It's not loose like this, but it could be. It's still a current carrying loop of wire. But if you take that and you cut it in half, let's say, then this is what it looks like. Let's say here's one of the wires, and we'll draw it like that. And then next to it is another of the wires, and we'll draw it like that. And then next to that one is another wire, and we'll draw it like that. So we've cut this thing in half, and the current that's going in is maybe going in on this end, going through the wire, coming out on that end, then looping back around and going in on this end, coming out there, looping back around, going in on this end, and coming out there. Okay, so what we did is we cut this current carrying wire in half, and we look at whether the current's going into or out of the wire here. All right, now this means that there's going to be magnetic fields associated with it because we have a current carrying wire. Of course there's going to be magnetic fields associated with it. So let's look at this first wire here and determine the direction of the magnetic fields. Well, down here at the bottom, the current's going in, so if you grab the wire, current's going in, that means the magnetic field lines are going around in that direction. They're going around like that, going around like that, due to that bottom wire right there. And then at the top, if you were to grab that wire, you can see that the magnetic field lines are going around like that, going around like that, going around like that. So, and that's true for every one of these, that they're going to have magnetic field lines going exactly the same way that I had it drawn in this first set. So that one as well, and this one in the other direction. There. Now think about how these magnetic fields interact here in the center. In the center, the magnetic field to this bottom one is going in that direction, and the magnetic field due to the top one is also going in that direction. So we've got magnetic field due to the bottom going that way, magnetic field due to the top also going that way. So all the way through the center here, there is a constant uniform magnetic field here. This, in fact, is a way that you can create a constant uniform magnetic field. You can have a loop of wire, and then in the central region there, you're going to have that constant uniform magnetic field. So the field lines look like what we've got drawn here. Now, for an ideal solenoid, B is going to be constant and uniform at the center. And the magnetic field on the outside is going to be 0. Now, that's an idealized case. So at the center, B equals constant and uniform. On the outside, B equals 0. Now you might say, well, how can that be? Well, look here. Let's continue to draw these lines, getting bigger and bigger. On the outside here, due to this bottom wire, the magnetic field lines point that way. But due to the top one, the magnetic field lines point that way. So they do work to cancel each other on the outside. They add together on the inside, but they cancel each other on the outside. And if you did that same sort of thing down here, you'd see they work to cancel each other down here. So we've seen that for an idealized case, B is equal to 0 on the outside, B is equal to the constant uniform value on the inside. But now what is that? In other words, what's the equation for B going to be for a solenoid? All right, let's set that up this way. Let's say that we've got a very tightly wound solenoid, but across the top here, all of the wires, and once again, we've cut it in half. So these are wires across the top, and there's one. Let's say they're square wires, because it's easier to draw. Each one of those represents then a wire that's coming out or going into the page. Maybe it'll make more sense when I draw the bottom half. And now down here is the bottom half of that. And ever how many we've got up here, we've got just as many down here. Now, I'm probably going to mess it up. So here's the point. Let's say the current is going in down here on that wire. It loops around the back side and comes out at that wire. Then that current comes out, loops around this way, and goes back in here, and then comes out up here. Goes in here, comes out up here, goes in here, comes out up here. And you can see what's going to happen here. This is the loop. You're looking at the top portion here, and this is the bottom portion. So if I were to draw the rest of it outside, it would look something like that, but I'm not going to draw all the center pieces here. Okay, I'm going to put X's on everything here so that we realize those are all currents going into the page. And these are all currents coming out of the page. Like that. All right. Now, this is a solenoid, so outside of the solenoid, this is idealized case, B is equal to 0. The question is, what is B equal to on the interior? And on the interior, it's going to be constant and uniform, but what is that value? Okay. All right. Well, in order to figure that out, what we need is a little bit of information. First of all, let's say that this has so many loops per centimeter. So let's say little n is equal to the number of loops per length. So loops per centimeter or something like that. And let's say that we want to figure out magnetic field on the interior. What we can do is we can draw an Amperian loop. So let's use Ampere's law to figure this out. Now here's the easiest thing to do. Take your Amperian loop and make it a rectangle like this, and enclose a certain number of those wires. Okay, so there's our Amperian loop right there. Now our Amperian loop has corners, let's say A, B, C, and D, like that. And let's say this length right here, we'll call that H. We can do the same thing on the sides, but you're going to see it doesn't matter. Those are going to cancel out. And now what we can do is decide which direction we want to traverse this loop. Well, if you look here, the currents are coming out, so odds are, to avoid any kind of sign problems, let's traverse the loop going in that direction, around like that, so in a counterclockwise direction. All right, now that we've decided all of that stuff right there, these are going to be the currents that are enclosed. Let's write down Ampere's law. Now, closed integral B dot ds. We've got to go all the way around this loop here, so really we can write it this way. We can break that apart and say going from A to B of B dot ds. So that would be the portion of the loop that's from A to B, plus from B to C, B dot ds, plus from C to D, B dot ds, plus from D back to A, B dot ds. Okay, that's just the dot product there, and that's equal to mu naught times the amount of current that's enclosed, which we'll need to take care of that right there. All right, but you'll see we'll have to add all of these together in order to figure it out. At this point, let's look at I enclosed. Now, I enclosed is going to be I enclosed is equal to I naught times N times H. Now, we could just count the number of wires there, but let's say that this is some arbitrary length here. If I naught is the current that happens to be going into 1 here, so I naught is that first current right there, it's going to be the same I naught through every loop then. So it's I naught multiplied by the number of loops that we've got enclosed. Well, how many is that? Well, you take N, the number of loops per length, and multiply it by the length, which is H. So this N times H is actually the number of loops that are enclosed. So the number of loops that are enclosed multiplied by the current, that's the total current that's enclosed then. All right, so this over here, this right-hand side of the equation, becomes mu naught times I naught times N times H. Okay, now we need to deal with each of these dot products here. And remember, this dot product in each case is B times the cosine of the angle between B and ds. All right, so let's look here. Let's do our first one here. We're going from A to B, so we're just concerned with what's going on down here at the bottom. All right? Now, since we're just concerned with what's going on down here at the bottom, the magnetic field is going to be constant and uniform in this region, and the ds vector is going to be to the right. Well, what direction is the magnetic field going to be? Use your right-hand rule. If you grab, put your fingers in the direction of the current, your thumb points in the direction of the magnetic field, so it works that way as well. So, and you could do that with each of these wires. Okay, if I grab the wire, the magnetic field is going to point to the right. Think of that. Regardless of how I grab the wire, magnetic field is going to point to the right. You could do it the opposite way. Curl your fingers in the direction of the current. Your thumb points in the direction of the magnetic field. So either one of those gives you the same answer, that B points that way. If that's true, then the angle between B and ds for this first term is going to be 0. That means the cosine term goes away, and I'm left with B, I'm sorry, that's a yucky looking B, times the integral from A to B of ds. Okay, what is that right there? The integral from A to B ds is just B times H. That's the length of that segment from A to B. It's H. All right, now let's do this next term here, going from B to C. Well, in this case, the cosine term, the angle between the ds vector is always going to point in our direction along the loop. That's the ds. B points this way. So what's the angle between the two? The angle between the two is 90 degrees, and what does that do to the cosine? That makes it 0. So that second term is 0. Now let's do the third term, from C to D. Well, in this term here, the B is going to be 0 because we're outside of this. We're outside of our solenoid, and we're assuming it's a perfect solenoid, so B on the outside is going to be 0. And if B is 0, then this whole term becomes 0 as well. So the third term is 0. Then we come to this last one. We're going from D to A. And when we go from D to A, once again, the ds vector points that way. The B vector points this way. So what's the angle? The angle between the two is going to be 90 degrees. The cosine term is going to be 0. So this fourth term is also 0. But what does that mean? BH is all that's left on the left-hand side, is equal to mu naught I naught little n times H. Okay, if that's the relationship, then we need to solve for B, and we can do that just realizing that the H's cancel. So B equals mu naught I naught times n. So there we have the equation for the magnetic field on the interior of a solenoid. And this holds for real solenoids as well, as long as you stay close to the central region and this diameter is very small compared to the overall length. In other words, if it's longer than it is wide and you stay close to the center, then this is a close approximation to reality. Even though we made some assumptions here when we derived that, it's still a close approximation to reality. Well, notice some things about this equation here. First of all, the magnetic field that you generate in the center of this is really just dependent upon how tightly wound the wire is. In other words, how many loops per length you have. That's N. It's also dependent upon the current. So if I want to crank up the magnetic field in the center, all I need to do is crank up the current. And there's a one-to-one relationship here as well. So if I double the current, I double the magnetic field here as well. I could, add more loops, but typically once you manufacture the solenoid, you're pretty much set. So N doesn't typically change then. But so if you want to increase the magnetic field after this solenoid has been manufactured, your only option is to crank up the current. And doubling the current doubles the magnetic field and so forth. Okay, you can take a solenoid like this and you can wrap it around on itself. And when you do that, it's like you take a wire here and wrap it around like that and comes out there. You've created a special type of solenoid called a toroid. T-O-R-I-O-D, toroid. And a toroid is kind of the same thing, and the magnetic field on the interior is going to be the same thing, but you might want to write it a little different since you know the number of loops that can be found here. B equals mu naught I naught big N over 2 pi r, where this right here, that fraction, big N represents the total number of loops, and 2 pi r, that represents this radius here of the whole thing. So it'll be the central radius of your toroid. And if you look at that, that's number of loops per length. So the length is this circumference, that's 2 pi r, and N is the total number of loops. So really these are just two different ways to write the same thing. Big N in this case represents actual loop count. Little n in this case represents loops per length. But when you've got actual loop count divided by the actual length, that's just n right there. So they're the same sort of equation. All right, now a lot of times people ask me, how does this relate to the solenoid of a car? In a car, a solenoid is often used as part of a starter mechanism to start a motor in a car. And the way that works is, let's say over here you've got the actual motor that has some kind of gear attachment to it, and this is what engages the big motor of your car and turns it over in order to start the internal combustion happening. So this motor has a couple of wires coming off of it, and what you want to do is you want to connect this up to your battery. And over here, let's say this is your battery, your car battery. It's got a plus and minus terminal, and it's a 12-volt battery. So oftentimes what they'll do is they'll put a solenoid sort of attached to a switch. So this amounts to a fancy switch. Now, nothing is drawn to scale here. I'm just making it big so you can see what's going on inside here. But there can be a T. Solenoids come in a lot of different shapes, but I'm just going to draw one here. Not all of them look like this. Let's say we've got this T-shaped piece of metal. And here is another piece of metal, and over here is another piece of metal. Now, one of these wires will be hooked up to that piece of metal. The other wire of the motor, let's hook it up over here to that side of the battery. Now, we'll take this side of the battery and we'll hook it up to that piece of metal. So what you can see is if this T piece of metal could be pulled down, it would make contact here and the motor would turn over. All right, but the way that it's usually done is you have a solenoid down here. So let's say one wire of the solenoid coming up here, and then it's wrapped around that piece of metal there. And then the other end comes off here. All right, let's put this outside here. Let's connect this one up to that same wire right there. And then this one will go to a switch. Now this switch is your ignition switch in your car. So you'll turn the key or push the button these days and it'll make that switch go down. Okay, so that's your ignition switch right here. Now the other end of this needs to go around to the other side of the battery. All right, so here's what's going to happen. Remember, you've got a strong magnetic field here in this loop of wire, and that loop of wire is wrapped around that piece of metal. So that piece of metal is going to become magnetized, and it's restricted in its movement. It's going to move down. So you close the switch, the magnetic field comes on, this comes down, and then you've got it connected right here. Now, why do you do that? Well, because your switch here can't handle a huge current. You want your huge current to go to your motor, but your switch can't handle that, and you don't want to be touching a switch that could handle that. It would be kind of dangerous. So you close your switch, it engages the solenoid pulls this T down, then you're making direct contact between your motor and your battery, and it'll save your battery as well because it's not connected up straight to the motor then. Okay, so that's a car solenoid. So the thing that's inside here is pretty much the same thing that we've talked about. It just looks different. The whole mechanism, if you went to an auto parts store, that would be considered the solenoid then. But it's actually the loop of wire inside that's the solenoid. Let's look at a single loop of wire and look at how it is considered to be a magnetic dipole. So let's say that I have a loop of wire. Here's a circular loop of wire, and it has some current going through it here. Well, use your right-hand rules, grab the wire, grab it on this side right here, and put your thumb in the direction of the current. The current is going around in that direction. Then here in the center of the loop of wire, there's going to be a magnetic field that's coming out at every point here on the inside. And if you did the same thing up here, you would discover that no matter where you grab the wire at, there's magnetic field lines coming up out of the page in the central region. So you could illustrate that by saying, here's this loop of wire, it's got a current going around in that direction and a magnetic field be coming out right there. And those magnetic field lines would come out here and go in outside of the wire. So if you were to look at it edge on, let's say this is the edge of the wire like that, then the magnetic field lines would do something like this. Like that. Okay? Well, let's figure out what the magnetic field is due to a loop of wire, but not exactly in the center of the wire. We can do that too, but we won't start there. So we're going to look at a single loop of wire. As is our custom then, we could start with a single loop and then add more loops to figure out what the better answer might be. But let's take a loop of wire. We're looking at it from the edge here. And up here at the top, that's where the current's coming out. It's looping around, and then it's going in down here. All right, and let's say this is the center of the loop up to that point right there. This is the radius of the loop. All right, then along this axis, along this radial axis here, out some point, some distance away, let's say a point right there, and the distance to that point, then we'll call that the z direction. I want to know what is the magnetic field at that point due to this current carrying loop of wire then. The problem here is we can't use Ampere's law because there's no symmetry here that's going to allow us to draw an Amperian loop and do the problem. I shouldn't say we can't use Ampere's law. I should say it's inconvenient to use Ampere's law, and we're not going to get a perfect solution if we do. It's not going to fall out easily mathematically. But we can use the BS law. And the BS law is going to allow us to figure this out pretty easily. And the way we're going to have to do that is we're going to have to take this loop and divide it up into sections. In other words, we take this loop and we divide it up into little ds sections like that. And another one here, another one there, another one there. So we're going to divide it up into infinitesimally small chunks. And then we're going to use the BS law here. All right, now in order to do this, we need a number of things. First of all, this is what it looks like from the front, but here from the side, we need to know the distance from here to that point. So that distance right there is r. And you know there's going to be a relationship here that r is the hypotenuse of a right triangle. Z squared plus big R squared is going to be little r squared. Okay, you can see that pretty easily. Also notice that theta in the BS law, let's write down the BS law here, that dB is equal to mu naught over 4 pi times I ds sine theta over r squared. This is the non-vector form of the BS law. In the vector form, there would be the cross product on top, but we know the direction of the magnetic field in this case, so we don't really need that at this point. Where the ds is going to point out of the board here, out of the piece of paper at the top. The ds is going to point in at the bottom, so if we're looking at it from the front, ds at the top, ds at the bottom then. And r, vector r, is going to point in this direction, so that's vector r. Its length is that way. So what's the angle between ds, out of the board, and vector r? The angle between ds and r is always going to be 90 degrees. So this 90 degrees theta, and think about it, everywhere along the loop that's going to be the case. If ds is going in to the page like that, r is right here, the angle, this angle, let me put this represents the r vector, my pen represents the ds vector. This angle here, that's kind of hard to see, this angle here is going to be 90 degrees. Okay? It's not any other angle, it's this one right here that's 90 degrees. And it's going to be that case anywhere along, so this is going to become 1 then. Okay, well, if that's the case, then we can probably figure this out pretty easily. We recognize that the total magnetic field at that point is just going to be the sum of the individual dBs. And when we stop to think about this, there's going to be a cosine term in here as well. And let me show you where that comes from. If you were to grab the wire and look at the direction of the magnetic field, out here at this point, the magnetic field is going to be in that direction right there. So if I take this and I break it up into components, I can have a component going this direction and a component going this direction. I know I haven't drawn those properly to length, but that's okay. This is going to be the dB cosine of an angle. Let's call that angle alpha, because this angle right here is alpha. And then this is the dB sine of, I did theta, alpha there. Now, if you do the geometry here, that angle is alpha. I know it's not real obvious, but spend a little time, you can convince yourself that angle there is also alpha. So dB can be broken down into two components. Now, based upon symmetry, for a component that's down here, a ds component going in, you're going to have the same set of coordinates here and the same alpha. And what you're going to discover is that the cosine terms are going to add to each other, but the sine terms, which would happen down here, are going to cancel each other. So that and that, those two components cancel each other, but the cosine components are going to add. So when we talk about dB being a vector, it is a vector, but it's going to ultimately boil down to just the cosine component of the vector that we need to worry about. And that's based upon symmetry arguments. So this dB total really boils down to dB times the cosine of alpha. All right, let's plug in our values now. Integral mu naught over 4 pi times I ds sine of theta, which is 1, times the cosine of alpha divided by r squared. Okay, the cosine of alpha, looking here, you can see cosine, this is just cosine of alpha, is going to be big R over little r. It's adjacent over hypotenuse, so that's big R over little r. And little r we can write as square root of z squared plus big R squared. So we can plug that in here, and this becomes integral mu naught over 4 pi I ds over r squared times big R over the square root of z squared plus big R squared. Okay, one other substitution we can do is this little r. Little r is going to remain fixed. Little r is not going to change here, so it's not really a variable for our problem, regardless of where you're at on the circle here. That remains the same. We can get rid of that, and when we do, write it in terms of z squared plus r squared. So let's do that. Integral mu naught over 4 pi I ds, big R on top, z squared plus big R squared to the 3/2 power. All right, now look at everything that's a constant. Mu naught's a constant, 4 pi is a constant. I is the current. I is not going to change in our loop. Big R is constant, doesn't change. Z is constant. Everything here is a constant except the ds. So all of this boils down to mu naught I big R over 4 pi z squared plus big R squared to the 3/2 times the integral ds. And that's it. So what's the integral ds? Integral ds is the circumference of the loop, and the circumference of the loop is 2 pi big R. So what happens when you plug that in? Mu naught I big R squared over 2 z squared plus r squared to the 3/2. Where did the pi go? Well, it disappears when you plug in the 2 pi r here. That becomes a 2 on bottom. Okay. And the big R, it's 2 pi big R, and that's where that becomes an r squared there. Okay, so there you've got the magnetic field some distance z from the center of the wire. That was some math to get there. However, it's not that complicated if you'll stop and think about it. The difficult part, in my opinion, is just trying to figure out the geometry here and envisioning it in 3 dimensions, even though you're forced to only work in 2 dimensions on a piece of paper. Imagining it in 3 dimensions becomes the difficult part for this problem and not this math. You can see the math reduced down to almost nothing. All right, but this is the magnetic field along that axis there. Now let me ask you a follow-up question here. Let's say the question is not what is B some distance out here, but what is the magnetic field right at the center of the wire, right at the central part? In other words, right here at the center of that loop. What is the magnetic field there? So here's our loop of wire. I'll draw it with some thickness. We know that magnetic field is going to be coming out of the wire, not out of the wire, but out of the board in the central region here, because we're going to assume the current is in that direction. Let's call it I naught this time. This is radius big R, and we're going to divide this up into segments, and each of those segments could be a ds segment. Okay, so we've got the current, and we know B at the center is going to be out. All right. If you looked at it from the side, it would look very much the same as what we just had. This is going to come out, this is going to go in there, and the distance from the center to the edge there is big R. Okay, dB equals mu naught I over 4 pi ds cross R. So this is what it looks like in the vector form over R cubed. Well, what you want is B, and that's going to be equal to the sum of the individual dBs here. And that's going to turn out to be 0 to 2 pi big R of mu naught I naught over 4 pi times ds sine of phi, and that's the angle between ds and little r. So this is going to end up being 1 over big R squared. Okay, so what does that boil down to? Well, mu naught I naught over 4 pi big R squared, those are all constants. And we're left with the integral from 0 to 2 pi big R of ds. Once again, that's just the circumference of the circle here, which boils down to mu naught I naught over 2 big R. Now that's B for one loop. If I want to add loops to this, if I add an additional loop, it just doubles that. If I add 3 loops, it triples that. So you can add an n here for the number of loops, and that's what it looks like at the center. Okay, we'll stop there.